So another kind of transformation that you can see associated with these sinusoidal curves would be a shift of the midline. We'll refer to it as a midline shift. Now, in terms of transformations, we'd be talking about the same sort of thing as a vertical shift. A vertical shift is the only thing that can move a horizontal line. So with that in mind, the two different versions of transformed sinusoidal curves that we had were the following, depending on what the mother function was. So this was a times the sine of omega x and a times the cosine of omega x. As soon as we tag on a vertical shift, this would be plus b, where b is some, constant. So the midline shift is going to be add b to the y values. Now, in terms of when to do this as part of the process, this is going to be the very last transformation. The reason being, the order that we had associated with transformations was horizontal shift, stretching and shrinking, reflecting, and a vertical shift. Vertical shift is always the thing that comes last. It also lets you know that the midline in both of these cases is going to be transformed into the horizontal line y equals b. If you say that the midline is b, you're not technically correct. The midline should be the equation of a line, and I should see a b associated with that. So for an example of a problem with a midline shift, I would like to try out the following graph using transformations. And we'll show at least two cycles. I'd like to do y is equal to 5 minus 3 times the sine of 3x. Now, first thing I'm going to do is reorder this in a slightly different fashion so that it better demonstrates this form that we see up here. So our a value is going to be negative 3. That 5 is positive. I'm going to put it at the end of the statement rather than at the beginning of the statement. Now we'll still see an amplitude modulation as well as a frequency modulation associated with this. So for the amplitude modulation, this comes from the negative 3 that's in front. So this will be multiply y by negative 3. Also lets us know that our amplitude is going to be the absolute value of negative 3, which will be positive 3. So in addition to the stretch by a factor of 3, we're also going to see a reflection. For the frequency modulation, we'll take a look at one period. And note that one period will go from 0 to 2 pi. The thing that goes inside here will be our angle. Our angle in this case is 3x. Whatever step of algebra I do to solve this, that'll be the same as what I do for my transformation. So the one step of algebra is going to be multiply by 1/3. So multiply x by 1/3. Also lets us know that a period is going to start at x equals 0 and it will end at 2 pi over 3. So the length of one period, or one wavelength, is going to be 2 pi over 3. Now, I didn't do this earlier, but it should probably be pointed out that the mother function that we have associated with this would be y equals the sine of x. So when we go over to our next sheet of paper, we'll know where those points are coming from. And finally, there will be a midline shift, and that is going to be designated by the plus 5 that we have here. So we are going to add 5 to the y values. Also lets me know that the midline is going to be the horizontal line, y equals 5. Not just midline equals 5, but the midline is y equals 5. So let's take all of this information, see if we can bring it over to the next sheet of paper, and graph it all. So I want to start with my mother function, y equals the sine of x, and we'll get the points associated with this. X coordinates will be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Corresponding y coordinates for the sine function starts with 0, then 1, then 0, then -1, then 0. We're going to have one horizontal transformation. We are going to have two vertical transformations, both in amplitude modulation and the midline shift. We'll start over here with the frequency modulation, where we're multiplying by 1/3. Now, I am going to be multiplying all of these fractions by an additional 3 in their denominators, but I am going to also reduce wherever appropriate. Now, the work that we had on the other sheet said that a period should start at x equals 0 and go to 2 pi over 3. I'd like to point out, though, we have a lot of different denominators in here, and with a lot of different denominators, I would like to express them all in terms of the same denominator. Lowest common denominator in all of these cases is going to be 6. So, for my pi over 6, I'm okay to leave that as pi over 6. Pi over 3, I multiply by 2 over 2, and we call that 2 pi over 6. Pi over 2, we'll multiply by 3 over 3 to get 3 pi over 6. And for 2 pi over 3, that will be 4 pi over 6. So this probably flows a lot better than these angles, but you can call them 0 pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6, and 4 pi over 6. That lets us know that the x scale that we'll want to use for this, once we actually graph, each of those tick marks will represent pi over 6. Next, we go to our vertical transformations. We'll start with the amplitude modulation. Amplitude modulation was we're going to multiply everything by -3 to increase the amplitude to 3 and reflect. Zeros will stay as zeros. +1 will become -3, and -1 will become +3. So it should look like a pretty standard problem so far, but now we have the midline shift. This is where we are going to add 5 to all of our y values. So each 0 will become a 5. -3 will become a +2, and +3 will become +8. So let's try and graph all of this together. I mentioned just a moment ago that I want the x scale to be pi over 6. Though I'm usually a stickler for reducing your fractions as much as possible, I'm going to say you don't necessarily have to in this case, just because it's going to flow much more nicely if we leave them all unsimplified. So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, that'll give us our first cycle. For the second cycle, 5 pi over 6, 6 pi over 6, 7 pi over 6, and 8 pi over 6. Now for my y scale, I'm trying to get y values that are 2, 5, and 8. So what I'm going to do is just make my y scale equal to 1, and we'll go up one at a time. Now for the sake of a nice consistent graph, I'm actually going to put a little dashed line in here to represent the midline that we see up here at y equals 5. So in order, our points are 0, 5, so start at the midline, pi over 6, 8, 2 pi over 6, 5, 3 pi over 6, 2, and 4 pi over 6, we're back to the midline. Let's try to make this sinusoidal curve look as nice as possible. We'll start at local maxima or local minima and bend them into the midline, like so. So that gives us our first cycle. To get a second cycle, we'll use the periodic property and say that these points will just start repeating themselves. So for the next point, up to a maximum, back to the midline, down to a minimum, and back up to the midline. And then curves just so elegantly back into that midline.
Damn, that's looking pretty good.
Hey girl, hey. So as an added bonus on these problems, let's determine the domain and the range. We've only drawn 2 cycles, but we know that this thing will extend infinitely in the left and right directions. For the range, the lowest value that I see is 2, and the highest value that I see in the y direction is 8. So the range on this bad boy is going to be from 2 to 8.